So, welcome to week 10, lecture 3 of probability theory with actuarial applications. In the last lecture, we have seen policy feature 1, deductibles. In today's lecture, we are going to discuss policy feature 2, which is policy limits. Now, let us understand the context from which this feature has come. So, in actuaries, what happens is if you are having enough bracket for actuarial applications, that initially you are not paying, but after that if some huge catastrophic loss comes, then how can you tolerate it, right? For that it is important to have the upper limit on how much amount you are paying, because in the last lecture also we made it clear that what we are worried about is not ground up loss, we are worried about the actual insurer payout. Okay. So, when we looked at lecture 2, when we are discussing deductibles, we are trying to protect the insurer from small and frequent losses. What if the insurer wants a protection from a catastrophic loss? For example, if there is a fire breakout and the insurance is supposed to pay 50 million for a single fire, then how will you protect yourself? So, answer to that is no, do not pay unlimited. In deductibles, we were keeping the cap, now you limit the cap on the upper side also. So, that's what we are doing today. So, what we will do is we will define a policy limit, which means the maximum amount the insurer is obligated to pay for a single loss. Okay. So, if the policy holder is responsible for all losses above this limit, insurer does not have to pay from his pocket. Okay. So, now what happens, what is the benefit of this? This actually tells you that your risk as the insurer is finite, you will never pay beyond a certain limit. So, it caps insurance losses. How it benefits the customers? Suppose somebody does not want to have an infinite protection, but happy with a certain protection. If you are giving a certain protection at a lower value, naturally your premium charges will be low, right. So, what this enables is creating policy tiers. So, we can have a budget policies where you are actually giving this lower limit, say health insurance giving you 5 lakhs, it is a lower limit, and then you have a budget policies where many people can opt for. Another one is it also allows me to give as an insurer premium policies with higher premiums, because remember what we were discussing, the conditionally how the area behaves or conditionally how people behave, that is what matters, and that is where this particular idea of policy limit is of significant help. Let us understand what is the theory behind this. Basically, the theory will be about the payout function Gx. So, let us understand how will you define Gx for this. So, what exactly is happening, that you understand first. There is a ground up loss and now you are capping that loss at some maximum level, that is what is happening. So, let us take few scenarios to make the situation clear. Let us call a scenario of a X, which is the loss distribution, being 10,000, but the policy limit is defined to be 50,000. In that case, whatever you claim will be given by the insurer. So, insurer payout is full, Y is equal to 10,000. Okay. In a scenario 2, let us say your loss is $1 lakh and the policy limit is $50,000. Then what will the insurer pay? Insurer pays only $50,000. If this goes to 1 million, still the insurer will pay $50,000. See the importance of this particular feature. That means no matter how big is the loss of the customer, you are bound to pay only $50,000. That is the idea of policy limit feature. So, how can you define it mathematically? This is the mathematical definition of a payout function. Y is equal to Gx, and this Gx is defined stepwise. It will be x up to a certain value, that threshold is called L or a limit. So, x less than L you will pay x, x above L you will always pay L. So, this is actually a mirror image of deductible, which is y equal to minimum of x comma L. So, you can write this function in a compact form as minimum of x comma L. Okay. So, how this looks like in the graph? You can see this. Okay. So, this is a graph which says that the maximum that we will pay is $50,000, and if it goes between 0 to 50,000 we will pay the actual loss. That is the idea of this graph, and you see how nicely the payout is. When we were dealing with deductibles, we had a threshold like this somewhere, and then up to that point nothing was happening. After that it was shooting up, right. So, you can easily compare the two graphs. Now, what we are doing? We are sealing at the top. So, this payout is the equal to the loss until it hits the ceiling L. L is the ceiling. So, what is of interest to us? If we are selling such a policy, what should be the premium? So, for that what should we calculate? We should calculate the expected value, which is very natural, and therefore, how will we calculate? The answer by this time should be clear to you. We will use the lotus for calculating this policy limit. So, a loss distribution has PDF fx, so we are assuming continuous, it has a policy limit L. What is the expected insurer payout? How will you answer this question? You essentially put in all the values of Gx and try to compute it. So, let us do that one by one. So, what was my Gx? My Gx was essentially x for x less than L, and it was L for x greater than or equal to L. So, how will I compute expected value of Gx? So, that is the idea. So, it is expected value of y, which is equal to expected value of Gx, and then we already know this expected value of Gx by lotus is integral minus infinity to infinity Gx fx dx, right. Now, how did we handle deductible? It basically we want to split this formula into this boundary, right, either less than L or greater than L. Let me go back to the So, over here I will break the integral, that means here I will break the integral, here it is a triangle, and after that it becomes a rectangle. That is what we need to do. Minus infinity is irrelevant, so it will be integral 0 to L Gx fx dx plus integral L to infinity Gx fx dx. What is the advantage of splitting it into two parts? I have a specific function, known function. So, this Gx is actually x and this Gx is actually a constant L, right. So, I have this kind of formulation. So, what I need to worry about is then this is integral 0 to L x fx dx plus L times integral L to infinity fx dx. Can you identify this latter term with some function that we already know? This is actually the survivor function of x at L. Okay. So, I can identify this particular function as a survivor function of x at L. So, I can rewrite this formula as integral 0 to L x fx dx plus L times Sx of L. Okay. So, this can be a simplest version of my expected value of y. Let us understand it step by step in a way I have written it or printed it here. So, basically what I did, I used the law of law of the unconscious statistician and evaluated this function. This was our indication. After that I started with this, I have taken the constant L out and expressed it in terms of survivor function. That is the idea. So, your expected payout formula, which this wedge actually or hat actually denotes minimum of x and L, and if I have this kind of payout, then expected value of y can be easily calculated through this formula. But wait, there may be a simpler shortcut, because this x fx is still difficult to calculate in some cases, right. So, can I have a shortcut to that? The answer to that comes from basic understanding of a non-negative random variable. So, when I have a non-negative random variable, I can easily compute expectations via survival function. For example, if I have a non-negative function x greater than or equal to 0 and I am looking at this integral from 0 to infinity x fx dx, I can actually use my knowledge of calculus and write this as integral from 0 to infinity and integral from 0 to x and say dt fx dx. So, you just look at this particular version, which is integral 0 to x dx, and now I can actually look at this as, so this is say t, this is say x, then this is a line t is equal to x. If I am covering integral 0 to x in dt, what does it mean? Where am I? So, I am here. Okay. Now, if I want to reverse the order of integration, that means what? I want to cover this region, but I do not want this particular function, but I want this to be calculated in this way. Then what I am calculating? I am actually looking at x, right, and this x will go from t to infinity. So, that is what I will do. I will swap this order of integration, and this particular thing which was with respect to t equal to 0 to x, x equal to 0 to infinity. Now, t will come out and it will go from 0 to infinity, and this particular thing which is x will go from t to infinity fx dx. And when I look at this formulation, what is this? This is actually your survival function. So, this becomes, so this actually becomes your survival function with respect to t. So, it is s x of t dt, an integral from 0 to infinity. That means what? If I am talking about expected value of x for a non-negative random variable, I can also talk about it in terms of entirely in terms of survival function. Okay. So, with this idea, can I do something better for this formula? The answer is yes, I can do. So, what is the idea? If I apply a non-negative random variable, I can show that expected value of x is nothing but survival function of x integrated from 0 to infinity. I can apply this to the new variable, which is y, integral 0 to infinity sy of y dy, because it is a non-negative random variable. And when I do that, I have to account for the regions that are created by this minimum of x comma L. So, the first region that I am worried about is when my value of y is greater than or equal to L. This is going to be impossible because it is minimum of x comma L. So, that survival function will have a probability 0. So, survival function will have a value 0, right. Then if y is between 0 and L, very simple, that means my x is greater than y and L is actually greater than y, right. So, both of them are greater than y. Since y is less than L, which is already true, this reduces to only probability of x greater than y. Okay. So, in this region I have probability of x greater than y. So, how will this formula translate? It is very simple. You write integral 0 to infinity syy dy, break it into 0 to L, L to infinity. Above L, this is an impossible event. So, this Sx is 0 and that becomes 0, and then what remains is simple, integral 0 to L Sxy dy. So, in particular, if I want to convert this in terms of x, which is minimum of x and L, right. So, it is integral 0 to L Sxx dx. Okay. That is the beauty. That means what we have is we can use two ways to price the limit. One way is actually using the density and x fx formula, if that is feasible. So, this is the standard formula where you can easily compute this if fx is simple. If survivor function is simple or CDF is simple, you can use this formula. Okay. Can you find an example in our named distributions where this becomes very simple, where the survival function is very simple? It is exponential distribution, right. So, there it is e raised to minus lambda x, just like that. So, when I have exponential distribution, this formula is actually very handy. However, if I do not have exponential and the formula for fx is simple, I can use the formula 1. Let us solve one problem for exponential case and illustrate how this will become handy. So, I have x following exponential lambda. I want to find minimum of x and L. How will I find? Simple, I said its exponential is easy. So, do I know what is Sx of L? The answer is yes, I know, it is e raised to minus lambda L. It does not depend on L actually, it can be anything. Sx of x is e raised to minus lambda x, right. In particular, L becomes this. Now, what I need to do, if I want to compute this expected value of x, minimum of x comma L, I need to integrate this over 0 to L e raised to minus lambda x dx, and exponential integral is very easy. So, it is e raised to minus lambda x divided by minus lambda evaluated from 0 to L. So, when I evaluate this, I get this 1 by lambda will be thrown out, minus sign will take this out, and 1 minus e raised to minus lambda L, correct, and that is my answer, right. It is so easy, in just 2 steps you are getting the answer. So, what are the steps that I have done? First, I know from my memory that Sxx is this, and when I apply this to integrate from 0 to L, and I got my answer. So, what is the logic here? Expected value of x is 1 by lambda and the CDF of x is 1 minus e raised to minus lambda L, right. So, if you look at this particular function, you actually can see this expected value of minimum of x and L is expected value of x into the CDF at L. This particular formulation is very convenient to understand and very easy to memorize when I have exponential distribution. Okay. So, this actually makes sense because it saves lot of our time when we are actually solving the problems. So, always remember, when it is easy to find survival function, policy feature 2 gives you an easy formula for finding it. So, what we have done so far, let us summarize. We have defined the second feature, which is insurance policy limit, and therefore our payout was defined as minimum of X and L. To calculate the premium for such a policy, we deployed our expected value formula or lotus, and from that we got the formula. Formula number 1 is integral 0 to L x fx dx L times Sxl. Okay. Second formula, which was a survivor shortcut, and that is integral 0 to L Sxx dx. And the third special case, which is exponential shortcut, which is very handy while solving the problems in exam, is expected value of y is equal to 1 by lambda 1 minus e raised to minus lambda l. You can also write this as expected value of x, and this is f x of L. So, that is the, when exponential thing is coming, it is very simple. What we will do now from this point onwards is very interesting. We will actually use the knowledge which we have got in this lecture and the previous lecture, and we will apply it to a policy which is the real world policy, which has both deductible as well as the policy limit. And with both of them, how will we define a real world policy layer? That is what we will see in the next class. See you in the next class. Thank you.